Do you think I should date this?
Sure. Yeah. Sure.
Yes.
Do we want to feel it's a young girl I dated a few years ago?
We'll be able to compare it to the other historic copies. There's one with Ben where he's got dark hair and then one with white hair.
Oh, yes.
We should watch those sometime in one of our classes. I think he did some lectures at the, was it the University of
Pick one.
Do these doors lock when they are?
Welcome everyone. Today we're going to discuss the most frequently used method for estimating the parameters of the Rasch model. In other words, finding out people's abilities and items' difficulties. And we're going to use the method of maximum likelihood, which was devised by Ronald Fisher around about 1919, 1920. So we'll start with just a simple example, and you'll find that a lot of what we do is actually just common sense. Let me start by drawing a line, which is our latent variable, imagination of how whatever it is that we are measuring works. And if we think of it like a yardstick or a tape measure, tape measures have lots of features that correspond to the sort of variables that we have in social science. Because a tape measure can sort of be of any length, and it has to be maintained. If we don't look after it, it won't stay very straight, and we have to keep fiddling with it to keep it along in one line, a unit dimension. And even when we think we've got it in one line, when we take a look at it, we notice that it's a little kinked and bent. But nevertheless, in spite of all its flaws, we find tape measures to be very useful measuring devices. So this is our imaginary measurement device, and we're going to imagine that it's marked out in equal interval units by, let's think for the moment, about a 5-item test. And we'll just use dichotomous items. That's just right, wrong, yes, no, true, false items. And we'll imagine that we already know where the items are on this variable. That's the sort of thing we might run into when we're doing computer adaptive testing, or when we're using items from an item bank, or from a pre-calibrated instrument. And we'll imagine the items are located at 1, 2, 3, 4, and 5 logits along this variable. Logits means log odds units, but also it has many other derivations if you can look back through the literature. And the idea, though, for using the logit, the log refers to natural logarithms, and odds refers to the odds of success. But let's imagine we have this 5-item test, items 1, 2, 3, 4, 5, and it's taken by 2 people. George and Mary. Now Mary does what we expect. She succeeds on the easier items and fails on the hard items, so that her raw score is 3 out of 5. George does something a little different. He fails on the easiest item, he succeeds on a couple more items, fails on the 4th item, and succeeds on the hardest item. This is the easy end, and this is the hard end, and his raw score is also 3 out of 5. Okay, let me just ask you just a common sense question. Okay, who has the greater ability, Mary or George? All right, Mary got the 3 easiest items right and the 2 hardest items wrong. George got the easiest item wrong, but the hardest item right. Right, we have a sample of 15 people watching me right now. Let me just take a survey. All right, how many vote that Mary has got the greater ability? Nobody's voting for Mary. What about George? Does George have the greater ability? Oh, well, about 1/3 of the people voted for George. 2/3 of the people didn't vote at all. All right. Well, of course, I know why, because people were beguiled by the idea that George got the hardest item right. But of course, in real life, I really hope that George is not my nuclear power station operator, clinical technician in the surgery, the bus driver, anything where doing the easiest thing, you better get right or else there's a disaster. You know, for instance, for a nuclear power plant operator, the easiest thing should be to know how to shut the power station down. Because if you can't do that, we may be in real trouble. You know, for the bus driver, he better know where the brake is. It doesn't matter if he can balance the bus on 2 wheels. The hard item, you better get the easier item right. So in many, many situations, in fact, failing on the easy item is a disaster. But I know in typical things like arithmetic tests, we would say, well, how could George fail on 2 + 2 = 4 if he knows how to do long division? So in that case, we're actually applying different sort of logic to this. We're saying we will ignore this wrong answer, and in fact, we'll give George 3 out of 4 on a harder test. In which case, if that's what we're doing, George does get the higher ability measure. But in fact, under the method of maximum likelihood, as I've demonstrated to you, both of these response strings achieve the same ability measure, but with different fit statistics. With different likelihood of occurring, Mary's is an expected response pattern, George is very unexpected. But the ability level is predicted to be the same, estimated to be the same. So let me think about maximum likelihood estimation from 2 approaches. One is that we need an ability estimate. We'll think about Mary for a moment. We need an ability estimate for Mary which predicts the score that she made, 3 out of 5. Now, as we're going to look for an ability estimate for Mary that matches the score that she made. Well, she made 3 out of 5. Now, this is the way that essentially all Rasch estimation programs work, particularly when they already have estimated the item difficulties. If they've already estimated the item difficulties, there are various ways of doing that. But once those are estimated, and then in the second cycle they go back to estimate the person abilities, they nearly all work this way. We look at this and we say, well, here's a set of items. Let's pretend we don't know where Mary is. So what we'll do is we'll make an intelligent guess. We'll say, okay, let's pretend Mary's ability is right here in the middle. All right, at 3 logits. And we will work out what is her expectation, what's her expected score, what's her probability of success on each of the 5 items, then add up those expectations to find out what her expected score is. Now, some handy cheat sheets. In the back of many computer manuals, for instance, this is the one for the Winsteps computer program, there is a table that relates log odds units to the probability of success. Around about in the book Best Test Design at page, what page number is this? Around about page 36 or so, there is a table that also relates log odds units to the probability of success. And for this group here, who are especially fortunate, I've put together a page of numbers so they can all help me do the arithmetic here really speedily. So we'll refer to this page. All right. When Mary takes an item, Mary at the moment, we estimate her ability to be 3 logits. And there is an item whose difficulty is 3 logits. All right. What's her expected score on this item? If this was the only item she took, what do we expect her to score on this item? Yes. If the ability of a person, this is her current estimate, matches the difficulty of the item, then she's targeted, at least in our minds at the moment, right on the item We don't know whether she's going to succeed or fail. So you can say the probability of success, or the expected score, as this is a dichotomy, is 0.5 score points. What about on this item of difficulty 2, which is one logit less difficult? In other words, she's one logit smarter than the item is difficult. And refer to your sheet. And what is her expectation? What's her expected success? Can someone tell me?
20%, very easy.
Okay, it's easy for her, so it's got to be above 0.5. Now, on the other hand, this one is harder for her. The one that's at 4 logits is one logit more difficult than she is able. So what's her expected success on this? 0.27. That's right. So you'll notice that she's got about a 3/4 chance of success, about a logit below. In fact, to get to 0.75, that would be about 1.1 logits below. And this is symmetrical. So 2 logits, when she's 2 logits smarter than the item, what's her success? Predicted success. Someone looking at their sheet? Pardon?
0.88.
0.88, yes. And when the item is 2 logits more difficult, what's her success then? 0.12. Okay, so here we have predicted a probability of success, which is the same as her expected score on this dichotomous item. We can imagine if she took this easy item 100 times, we'd expect it to succeed 88 times and fail 12 times. So on average, her expected success is 0.88. When we add this all up, we find that her expected success on these items adds up to 0.88 plus 0.73 plus 0.5 plus 2.7 plus 1.2, which had better come out to 2.5. Well, that makes sense, because we expected her to succeed on the low ones, fail on the hard ones, and in the middle it's a toss-up. All right, well, but her actual score is 3. Her current score is 2.5. Oh, well, in that case, we had better, what had we better do to her ability estimate? Move her. Make it higher or make it lower? What do we think? Is she smarter than we thought? She's smarter than we thought. That's right. We thought she had an ability of 3. That produced a raw score of only 2.5. Her actual raw score is 3. So we need to increase this. All right, what should we try then? This is called an iterative method. We're going to increase her ability estimate. We're going to move it up. And we don't know exactly what it should be, but we can make a guess. Now, I'll show you in a moment how the computer makes a guess. But what would we guess? What would we guess is her ability? What would you say?
3.4.
3.4, 3.5? Well, 3.5. Well, let's try 3.5. 3.5 is an easier number. All right, so we think, well, we'll move her up. We're too low. If we moved her all the way up to 4, that would mean maybe a little bit too much. A whole logit would mean that maybe we expect her to succeed on 3, fail on 1, and 50-50 on the other. That would give her a score maybe around 3.5. So that sounds a little bit too much. So maybe if we update her ability estimate to 3.5. So she's now right here. And we'll do this again. 3.5. Whoa. All right. Okay. She's 2.5 logits smarter now than the easiest item. She's at 3.5. The easiest item is at 1. So what's her probability of success expectation? 1?
0.92.
0.92. All right. She's 1.5 above this. 1.5 logits. It's got to be above 0.5. 82. Got it? 0.92, 0.82. Now we're half a logit above it. Ah, okay. Now we're half a logit below. That'd be 3.8. And now we're 1.5 logits below. That'd be around 0.18. Is that right? And my fast calculator operator is going to add 0.92 plus 0.82 plus 0.62 plus 0.38 plus 0.18, and that's going to add up to 2.92. Is that right? Good. Now we're getting close. Our current estimated score for her is 2.92, and our actual score is 3. So this is called converging. We're converging, we're getting closer on between the expected and the observed. So now we need to make another adjustment. Right, so now we'll make the adjustment using the method that the computer does. We were just doing this first adjustment just by common sense, seat the pants. So how does the computer know what adjustment to make? Well, this is the probability of success for these dichotomous items. And Bernoulli discovered, I never lived, way back, just before around about 1700, that associated with each of these probabilities there is a variance. And the variance of a dichotomy is the probability of success times the probability of failure. So if 0.92 is the probability of success, what's the probability of failure? Pi is 0.08. All right. Now, in order to speed this along, what I've given you, for those people right here, is on the other side of your sheet from the probabilities, it shows the variances. And this is a handy little sheet to make up if you've done this by, if you're planning to do this by hand. I just wrote a little computer program. You do this from your spreadsheet or something like that, which computed P1 minus P for all combinations. So we can do this computation very fast. So if you look up on the, I think 0.92 times 0.18, so we can see. Could you actually multiply 0.92 by 0.18 on your calculator there? What was it? 0.0736. Okay, well that's a precision at the end there, which is way beyond the precision I was using, so it's about 0.07. But if we turn over to the variance side, we should see that for something 2.5 logits away from the person, the variance shown should be 0.07. Is that right? Good. What about for 1.5 away? What's the value? On the variance side. 0.15? Yes, 1.5 logits away. Is that right? Okay, for half a logit away? 0.24, good. Now it's symmetrical, 0.24 and 0.15. Because P1 minus P is the same as 1 minus P times P. So this now adds up to the total variance. But this variance is also, it's called the statistical information in this. And this is where Ronald Fisher and another method called Newton-Raphson, which is actually what we're doing right now. This is called Newton-Raphson iteration. Newton-Raphson. And what that does is it says that if our new estimate is B dash, and we want to know how to go from our old estimate of ability B hat, then what we do is we take the observed score minus the expected score and divide it by total variance. Now in this case, the observed score is 3, the expected score is 2.92, and the total variance is the sum of each of these things. 0.07 plus 0.15 plus 0.24 plus 0.24 plus 0.15. And that equals 0.85. Okay. So that's 0.85. So maybe 3 minus, let's see, that was 292. So that's 3, this is about 0.08. 3 minus 2.92 divided by 0.85. Pardon? 0.09. Okay, so our last estimate was 3.5. This says the change should be 0.09. We notice the observed here is bigger than the expected, so this is going to add. So our next time around, we're going to move up from 3.5 to 3.59. It's going to be our next estimate of this person's ability. And we could go through this whole procedure again, now using an estimated ability of 3.59, and it would change just a little bit more, a very small amount, and this process rapidly converges to the point that the change from one cycle through this, one iteration through this to the next, becomes so small that it has no practical import. We're now starting to change things in very, very small, lower decimal places. So essentially, we found the answer. We found the estimate. Now, this would have worked exactly the same way whether we were looking at Mary or George, because their score was the same. Notice, as we're doing this, we're computing this part, the probability of success, based on an idea of someone's ability. We end up with a score at the end that has nothing to do with the actual way that they made their responses. And then we compare that score with the total score, which also has nothing to do with the way they made their responses. So what would happen for both George and Mary is that this process would yield the same ability measure. But what if we did take into account which ones George has succeeded on and which ones Mary has succeeded on? Right? That's actually the way that Ronald Fisher did it. And this is, we could say, a derivative result of the method of maximum likelihood. But what Ronald Fisher was looking for was the ability estimate for which the particular data that was observed was the most likely to be observed. So let's actually do maximum likelihood directly. What we've been doing here is a simpler computation, maximum likelihood indirectly, but we'll do it directly now. For convenience, let's just think of our ability estimate. Well, we can take the 3.59. 3.59 is our best guess at what the ability estimate of George and Mary is. But we won't think about that for the moment. Let's try some other ability estimates for George and Mary and see what happens. All right. Let's think about George and Mary having an ability estimate of just one logit. B equals 1. And we'll start with Mary. All right. If Mary's ability was 1, what's the probability that she would succeed on the first item whose difficulty is 1? 50%. 50%. 0.5. What's her probability that she would succeed on the next item, which is one logit more difficult than she is able? What's the probability she would succeed on this item? 27. Okay, what's about the next item, which is two logits more difficult? 1, 2. What about on the next? What about that she would fail on the next item? That's 3 logits more difficult. Fail on an item, it's 3 logits more difficult.
95.
Yes, 0.95. We expect her to fail on an item so hard. And what about failing on this one, which is 4 logits on the fifth item? 0.98. Okay, so what's the probability that we would observe this and this and this and this and this? Well, when we think of a probability of a whole set of events, that's called a likelihood. And the way we find the probability of a whole set of events is to multiply together the probability of these independent events, because we imagine these events to occur essentially independently, so that one doesn't force the next one. Yes?
What determined where you switch from probability of success to probability of failure?
Oh, whether she succeeded or failed. We're looking at Mary's particular response. She succeeded on the first 3, so this is the probability that she would succeed on the first 3, which got lower as the items got harder. And then that she would fail on the last 2, which got higher as they got harder. So we end up with this. If we want to find out the entire likelihood, and the Greek letter capital lambda, it's like some sort of a mountaintop igloo or something. No, is Could someone do, could you modification? You have it.
0.02.
0.023.
It's 0.015.
0.015. Multiplying all these things together. Is that right? 0.015. All right, let's do the same thing for her now with, but now we'll estimate her ability to be 2. All right, if her ability is 2, and this item, she succeeds on an item one logit easier for her, what's the probability of success? 0.73. Okay. Now we know this one's totally right on her, so it's 0.5. This one is one logit above her, so that's 0.27. This one she fails on, and is 2 logits above her. We expect her to fail. 0.88. Is that right? Good. And this one she fails on, and we expect her to, must be 0.95. All right, we have a new multiplication here. 0.73 times 0.5, 0.27 times 0.88 times 0.95.
0.082.
0.082. All right, so far what we've discovered is that the likelihood of the data, of this data that we observe, increases if her ability is 2 rather than 1. All right, what we're looking for, this is called maximum likelihood estimation. We're looking for the value of ability for which the likelihood of the data becomes the highest. We can see it's getting higher. 2 produces, an ability estimate of 2 produces a more likely set of data. Her result, the data we saw her make, is more likely when she's at 2 than at 1. What about when she's at 3? Okay, so that moves her 1 more up to, that was at 2, so this is at 3. I'm slipping up here, someone can catch me in a moment. Okay, so now we're at 3. Let's see, the probability of success on an item 2 logits below her, it must be 0.88, then times 0.73, then times 0.5, then she's got a 0.73 chance of failing on that one, and must be a 0.88 chance of failing on that one. We're beginning to see the same patterns.
0.206.
Oh, 0.206. Oh, things are getting pretty hot here. What about if we jump past 3.5 and go up to 4? We might feel, well, this likelihood is just going to keep going up and up and up as long as her ability keeps going up and up. The likelihood keeps going up and up. So let's backtrack to, let's jump up to an estimate of 4. All right, now she's up here. She's now 3 logits above this very easy item on which she succeeded, and her probability of success is 95, 0.88 times 0.73. She's right on this item here now. It's a toss-up whether she succeeds or fails, so it's times 0.5. And she fails on this item here, the last item. We expected to do that, so that's 0.73. What's this now gives us? 0.95 times 0.88 times 0.73 times 5. 0.5 times 0.73.
0.222.
Okay, 0.222. And just to try the whole range, B equals 5, ability equals 5. Wow, she's all the way up here now. 4 logits ahead on the easiest time. Now you can see why computers are necessary. To do this by hand, it gets very arduous, but 4 logits ahead. What was 4 logits by? Okay, 0.98 times 0.95 times 0.88. Now she's failed on an item a little bit on the easy side of her. So she's failed on this, and that must be 0.27 times 0.5. 0.988. 0.98 times 0.95 times 0.88 times 0.27 times 0.5.
0.110.
Ah, 110?
111.
111, that's good. Okay, so we can see that what's happened is this number's gone 0.015, 0.082, 0.206, 0.222, 0.111. So it's gone up and then it's come down. let's just try this, the value of 3.59, which is the value that we, using the previous method, estimated her ability at, and see what likelihood that gives. 3.59. So, okay, now we're really going to need help here. So it's the probability of success for 3.59 minus 1, which is 2.59 logits above the item. She succeeded on the